Welcome everyone to my talk on complex valued visualization. I'm kernel developer in the visualization team, and today I'll be showing you some of the plots that we've been adding to the Wolfram language to visualize complex functions. So the first slide here, actually, let me just skip over that. So this is the list of functions that I'll be showing you today. So I split them up into two groups. The first 5 functions are the ones that we've already added to version 12 of Mathematica, and the rest of them, we are working on them to release soon. So there are 9 of these functions, and I won't have time to go into all aspects of these functions. So what I did is I added a few resources in this slide. So there are 3 links. The first link will take you to what's new in Mathematica 12 page. So for every major release of Mathematica, we put together examples to show off some of the new features that we've added. And so this link will take you directly to the page on complex visualization. And so it has a bunch of examples, and you can drill down on any given examples, and it'll show you the application, it'll show you the code snippets, and it'll talk about the function and the options related to the function. The other 2 links here are for the talks that we've given in the past year about this functionality. So the first one is a talk that Brett Champion gave on Twitch earlier this year, which actually talks you through some of the examples on the What's New in Complex Visualization page. And the third link is my own talk from last year's tech conference, in which I showed the first group of functions. So I got a little bit more time to go into them than I probably will in this talk. So with that I can, so one more thing to say is that these are handy and convenient functions that we've added, and we build them on top of existing visualization functions. So, and the naming scheme should give you some idea of what the underlying function is. And most of the options that work for the underlying function should also work for the complex variant of that plot. And in cases where we needed to do something special with the input, then we've added new options for these plots, and I will point them out to you as we go along. Okay, so with that I can jump into the functions. The first one is complex list plot, and it's probably the simplest one. And it takes in a list of complex numbers, and it plots them on the axes. So here we generate a table of complex numbers by plugging in some values into the zeta function, and plot the real part on the x-axis and the imaginary part on the y-axis. And so we get this familiar looking plot of the complex numbers along the critical line. So complex list plot is built on top of list plot, and so you can use options like joined and scaling functions, and they will still behave like you would expect them to. So the next 2 plots are reimplot and abs arc plot, and these plots take a complex functions and do a few things with them to plot them. So reimplot plots both the real and the imaginary parts of the function. So while plot of a function like this will just give you the real part of the function, reimplot plots both the real and the imaginary parts, and it styles them differently. And so if you look at something like plot legends, this automatically knows that there are two parts to this plot, and it splits the legend nicely for you to be able to differentiate between the two parts. And I'm also overlaying these plots with the roots of the zeta function using epilogue. But the two options to note here are ream labels and ream style, which are new options for ream plot, which give you better control over styling and labeling both the parts that are the outputs to this function. Ab's arc plot will take the function and it'll plot the absolute value of the function, and then it will color the function based on its argument. So if you look at the legend on the right side of the plot, it will give you the key to read the color that is being plotted in the plot. So, so the bottom function which plots the ream on z, as you saw in this one, it's for this specific input, it's purely real, and so there is no imaginary part to that function, and so that's probably a bit easier to read here. There are only two colors going on, and you can pick the colors and figure out what the argument is for that plot. The top one is obviously the zeta function, which has more variation. Next plot is complex plot. This is a plot that is on the complex plane, and it takes the complex function and plots it, and then it does a couple of things. So first, let's talk about the color. It colors the function based on its argument. Obviously, just like for Ab's arc plot, you can read off the argument based on the color. If you have this kind of a coloring scheme, it so happens that we can also pick out some important features of the plot based on how the color changes around any given point. And so that's what the thumbnails across the top are showing you. So there are a few features cited. So if we look at the first one, which is a 0, so that arrow, the white arrow, is showing you the direction in which the colors are changing for this particular color scheme. So if we start off with the color that is corresponding to the minimum of the argument on the legend, the right-hand side of the legend, and then go around, starts off with that sort of turquoisey sort of color, and then it goes all the way around to the cyan-ish color. And so if you look at the legend, you can see both the endpoints, the bottom and the top. And then if we figure out in which direction the colors are changing, so that's sort of changing in the counterclockwise direction, which tells you that there is a 0 at that point. And if you if you skip one and look at the pole, the position of that cycle changes, and now the colors are changing in a clockwise direction. So that's how you can pick out zeros and poles. If you have multiple zeros and multiple poles, they will change the color multiple times depending on how many zeros and poles there are.
Is there an option to have the vertical axis be 10i, 20i?
You can do that with the labeling option for, yeah. And so, yeah, the final one is a singularity where the color cycles get faster, if you will, as you move towards the point at which the singularity. So in the thumbnail, you start from the bottom left. As you go up to the top right, as you approach the point, the colors cycle sort of infinite number of times, and then you sort of come out on the other side. So that's with a color. So you plot the function, you color it by the argument, and then we also sort of put another layer on top, which is a shading pattern. And so you kind of see that in this plot with the corners on the left side where you see the white where it's it's starting to clip. And so after the color is applied, the shading is applied based on the absolute value of the function. And so for the second example, for Riemann Z, I have specified a shading pattern that is not the default. By default, it shades based on the absolute value. And I've specified a different one. And the way to specify this is using the color function option, which takes a list, in which the first part is the color function, and the second one is the pattern that you want to apply. And so we have a few of these named patterns, which are in the documentation. And so I picked the cyclic log abs. And this gives us an opportunity to look at the second part of the legend on the right. So the legend is split into two parts. The right side gives you the colors for the argument, and the left side shows you the pattern that is being applied based on whatever scheme we pick. So in this case, we picked a cyclic log abs, so it applies the pattern based on the log of the absolute value. So you can see the log scale there. And it'll show you sort of where the cycles happen based on some criteria. Complex plot 3D is the last plot in this group of plots. And this is very similar to complex plot with just the difference that now we have an extra axis to plot the absolute value. So we go ahead and plot the absolute value directly on the z-axis, and we do not have any shading. And so here I'm doing the same thing as in the previous plot, but we have the absolute value being plotted on the z-axis, and I'm applying scaling function log to sort of smooth out some of the features so that we get a good sense of what's going on with the functions. So that completes the first group of functions that I showed you. This is the second group which we are working on. And the first one is complex region plot, which is very similar to region plot. So it plots the region where the predicate is true. And so in this case, we are plotting the regions where the imaginary parts of the function are positive. We are also adding complex versions of stream and vector plots, where the functions take the complex function and plot the vector fields. And so if you went to Brett's talk this morning, he talked a little bit about the improvements we're making to vector plot. And so we inherit those into complex vector plot. So here you can see the Riemann Z function where we're plotting the vector field, and you can get some idea of what the function is doing. So here the sizes of the vectors are constant. The argument you can sort of figure out based on the angle of the vectors, and then it's being colored based on the norm, and so it'll give you some sense of what the function is doing. So the final set of plots here are complex contour plots, and so we have the same sort of function here. So this plots the contours for the values of the function that is being plotted. And so here we have the imaginary part of the function, the contours for the imaginary part of the function that are being plotted. And we've introduced a new color function called balanced hue for complex plots to sort of balance out the variation in some of these values, so which also looks nice. So complex contour plot has another trick up its sleeve, which is that if you give it a list of functions, it will plot the contours for both functions. So you have the real of zeta and imaginary of zeta here, and the real imaginary for the Riemann z, and it'll plot both the contours together. And so in this configuration, it does not sort of fill between the contour lines with any color so as to sort of minimize the visual clutter that happens if you have this layering of colors. But you still get the idea of what the functions are doing, and it's an easy and good way to compare two or more functions at the same time. So I want to sort of close out my talk by showing you a couple of plots. So this is the sort of the 2D extension, if you will, of the Riem plot that I showed you earlier on. So we're plotting the zeta function, the contours based on the absolute value of the zeta function. We are applying a scaling function to it. We're applying the new color function. And then we're overlaying that with the roots of the zeta function, the non-trivial roots of the zeta function. You can see that line up with the critical strip. And the same thing with the Riemann z. And for these functions, the roots of the zeta function, the roots coincide. So that's a nice way. This is also sort of the famous contour plot from the Riemann zeta poster, if you are aware of that. And this is the complex plot 3D version of that. And so the absolute value is plotted on the z-axis. And we are applying the log function. You can see the ridges nicely for the zeta. And we are overlaying again with the roots for the zeta. So I think that's the end of my talk. So this is just to highlight the point that when we look at complex contour plot, this is really a mapping from complex to real, not from complex to complex. So you always have to, well, most of the time you have to have a function that will give you good values for the contours on the real. If you want sort of the traditional mapping for complex plots, you'd still have to use, we can still use parametric plot. This is the sort of conformal mapping for the zeta function, and this is the old-fashioned way of sort of doing the same thing. We don't have a complex version of the parametric plot yet, but I just put in this slide to highlight that point there. And so, I think I'll end my talk there, and thank you.